Hello, my name is Matthew Shack, and I'm here to present our work on robot team data collection with anywhere communication. We are considering the data collection problem, where a team of robots must collect data from static sites in the environment and then return it to a base station. These sites are represented by convex areas, shown as the light blue areas in the picture to the right. Our work's improvement over state-of-the-art comes from considering two things. The first being that we consider robot-to-robot communication, which shortens the time it takes for data to arrive at the base station. In the picture to the right, one robot goes into the environment to collect data from two wireless sensors and takes a picture of a point of interest. Then, instead of driving all the way back out, it saves time by transmitting the data through a wall to another team member. So robots must be able to reason about more than just visiting static sites, but also rendezvous points anywhere in the environment. Secondly, we directly attempt to minimize the arrival time of the last piece of data, or, in queuing theoretic terms, minimize the latency of the team. Formally, we define this minimum latency as the minimum of the last robot's transmission. This objective differs from other works, which attempt to minimize the total distance traveled by the team because it doesn't penalize parallel motion or transmission by team members. This objective better captures what we actually want, which is all data as quickly as possible. However, solving the data collection problem has its own set of challenges. The single robot case reduces to a traveling salesman problem, so it's at least NP hard, and TSP heuristic solvers find solutions that sum costs, rather than allow for parallel actions, like the minimum latency objective. The minimum latency objective is only really bounded by the robot with the largest latency. That means that the other team members can do whatever they want so long as they transmit all of their data back before the bounding robot. In the example to the right, where two robots must collect and return the data from the three upper sites, the robot on the right can take a longer path to go to S3 and back, so long as it arrives before the left robot finishes. Additionally, since all of our robots are homogeneous, we can switch which robot follows which path and get another optimal answer. These multiple global optima make it hard to directly optimize the problem, as state-of-the-art solvers use branch and bound techniques to prune necessarily suboptimal variable assignments. To address these challenges, we came up with a factored approach to solving the data collection problem. We separate our discrete decisions, handled in our tour generation, with the continuous motion required to accomplish those decisions, handled in the mixed integer linear program. We consider discrete decisions to be what site a robot visits and who a robot communicates with, and call the sequence of these decisions a tour. When we are reasoning about discrete decisions, it is easier to account for and identify equivalent optima before running the more computationally expensive mixed integer linear optimization. It also gives us a lower bound on latency, which we can use to declare global optimality. The discrete decisions are passed to a mixed integer linear program, which finds continuous motions required to accomplish the tour at a minimum latency, and we declare global optimality once our minimum latency is lower than the lowest lower bound. We performed experiments in simulation in 4 different environments using a 3-robot team. The environments differed in the amount of open space and the number of data collection sites. The maze and routes environments had many walls which we could transmit signal through, while the non-convex environment was more open. We compared against a state-of-the-art TSP solver called LKH, which attempted to minimize the vehicle routing problem's objective. However, LKH doesn't account for site areas, so we also compared against using LKH to generate a tour, and then post-processing that tour with our optimizer. It's important to note that LKH and LKH plus opt considered each robot independently, so we don't have any robot-to-robot communication. Additionally, we compare against using the mixed integer program directly, and then our 2-stage factored approach. We found that in all of our testing environments, our work had the lowest latency. It's not shown here, but LKH and LKH plus opt returned answers very quickly, since they're very good heuristic methods. But solving the vehicle routing problem doesn't minimize latency, so our work was able to find lower answers. The MLP in our factored approach ran until the 10-minute timeout, but our factored approach found better answers by discarding multiple optima the MLP had to consider. We also included an optimal method, which was running our factored approach for 12 hours. Both our work and the MLP computed lower bounds, where the MLP's lower bound was the linear relaxation of the problem. We used the difference between the lower and upper bounds to compute the optimality gap, shown in the table to the right. Solving the problem as one big optimization problem is computationally challenging, which resulted in a bigger optimality gap for the MLP compared to our work. This implies that our factored approach is a better way to think about the problem than just trying to solve it as one big optimization problem. In the future, we'd like to improve our factoring algorithm, specifically tour generation, to see if we can get better lower bounds and perform physical experiments in more complicated environments. Thank you.